In this video, we're going to see an application of an improper integral. And a lot of physics examples are sources for improper integrals where we want to take things out to infinity. And that can be field strength, it can be total force, it can be a whole number of different things. Here we're going to see it as a work calculation, which is something that we've done before. So if we imagine the Earth here, it has some defined radius, to the surface anyway, radius of the Earth. And what we can do is lift objects, like, say, rocket ships. And if we lift them up, one of the things that becomes of interest is how much energy would it take to lift not to some specific point, but all the way out of the grasp or the reach of the planet Earth. Well, we know that gravity actually goes on forever. The force is always defined. It just gets smaller and smaller. So the natural thing to evaluate out to is to infinity. Or to move a mass from the surface of the Earth all the way out to infinity captures exactly what we mean by the energy to escape Earth's gravitational field. All right. So why is this complicated? Well, anytime we have to do work, we can calculate that as force times distance. So we imagine we're moving out along that trajectory. However, the problem with that being a simple multiplication is that this changes as we move, or it's not constant. And if that's the case, then we have to handle it a little more carefully. If it's not a constant force, then we have to figure out some way to break down the calculations of force times distance in a way where the force is approximately constant along its trajectory. So what do? We imagine our Earth's surface here, and what we envision is being at a distance r, and then we're going to lift by, guess what? A small amount. Guess what it's going to be called? Delta r. And if we do that, then that means r is approximately constant. We don't actually change it that much. And that means that our force due to the gravity is approximately constant. And so we can use the force times distance formula. So the work to lift by some small change in r is going to be equal to our force times distance. And our force is g m1 m2 all over r squared, not r2, r squared. That's a g. And so that depends on where we are when we're lifting, but we're going to move by a simple little distance of our lift is delta r. And so we could figure out what's the force of gravity right now, and then multiply that by the little lift distance, and that would give us the amount of work done. Of course, if we want to find the total work to lift, now here's the fun part, from r0, that would be the surface of the Earth. We're not lifting from the center of the Earth, we're lifting from the edge, or the surface where we live, to, well, out to infinity. That would be easy to express as an integral. It's exactly the force we talked about before, all over r squared, and the only change is the delta r turns into our infinitesimal, our super tiny dr, and our starting values are r0 to infinity. And that'll be the work to lift some object from the surface of the Earth all the way out of Earth's gravitational field. All right, let's go evaluate that. We're going to keep it as symbols for now, and we're going to do our usual thing with our limits. We're going to have the upper limit be b. We're going to go from r0, g m1 m2 over r squared dr. Now, it's going to be helpful to rewrite this a little bit. These things are all constants, so we can bring them out front, g m1 m2, and then we have the integral from r0 to b of 1 over r squared, that's r to the minus 2, expressed as a power. Then we can integrate And when we integrate, we get still our limit. We're going to do that at the end. Limit as b goes to infinity, g, gravitational constant, the two masses, and this becomes negative r to the negative 1 between b and r naught. Then we do the sub in, b and r naught for r, the distance that the position that we're at as we're doing our integration. And sorry, that's a multiplication there. All of this times that. So limit as b goes to infinity, gets copied, gm1, m2, then this becomes negative 1 over b minus 1 over r naught. And this limit, fortunately, turns out to be nice and convergent, so it actually is a fixed amount of energy required. As b goes to infinity, this term goes to 0, and so we get the simple conglomeration of g, m1, m2, and this ends up being positive over r naught, not squared, just r naught by itself. And if we go grab our calculator and sub in all these values, we should get a number like 4.7 times 10 to the power of 9 joules, which is admittedly a whole pile of energy. So to lift something the mass of a person away from the mass of the Earth, this nice big number there, is going to cost us or take us or require from us 10 to the 9 joules. But admittedly, that can be a term or an expression or a value that's hard to interpret. What physicists came up with as an alternative or another way to visualize this is to look at how fast you would have to be moving. So imagine you're spiraling around the Earth here and then start moving up. Imagining, of course, no friction, no air resistance, that kind of stuff. But if you could trade the kinetic energy that you have moving around the surface and just aim upwards, and then just like going over a pole, if you're a pole vaulter, what energy would be just enough, or what speed would be just enough to get you to, well, here, infinity, that would define what we mean as the escape velocity, or mean by the escape velocity. And the fortunate thing about this is we're talking about energy in both cases. We're talking about kinetic energy, and we're talking about work, which is a measure of energy as well. So what we do is we set our work equal to our energy kinetic, or our 4.7 times 10 to the 9 joules, equaling 1/2 m here, and v squared. But the m is our mass, as our human being here, of 70 kilograms. And what that lets us do is solve for the escape velocity, the speed we would need to be going at the surface of the Earth, that if we turned it into potential energy, slung ourselves away, that we could actually escape Earth's gravitational field. And we end up with 2 over 70 times 4.7 times 10 to the 9 equals v squared, or a v of roughly 549 rather. And checking the units that we had before, joules, kilograms, and so on, this would be meters per second, or in more common terminology, 11.5 kilometers per second. So that is really, really fast. So these are impractical speeds at the surface of the Earth, typically with our limitations on air resistance and friction, those kinds of things. But that captures intuitively why it's hard to escape the Earth's gravitational field and actually launch something out into space, because of the high energy requirements, here more easily understood as a velocity element of kinetic energy. But escape velocity from the Earth, 11.5 kilometers per second. Computed, importantly, based on an improper integral, trying to assess how much work would it be required to lift something from the surface of the Earth, not to some fixed location, but all the way out to infinity, or beyond the reach of the gravitational field.